All right, today we're going to talk about what arithmetic and geometric sequences look when we graph them. So, quick review. And this is our formula for the nth term of an arithmetic sequence. And I've typed up an example here. So, here's an example where our first term is 5 and our common difference is 3. Okay, so let's think about this in terms of a function. Generally speaking, what would we input when we're doing problems like this? And what's our output going to be? Do we input the actual number for that term? Usually not. Usually our input is the n, and our output is then the number in the nth place, the nth term. So if we want to write this as a function and use x as our input variable, right, it would look like this, right? This is our output, this is our input. Let's see what that looks like if we graph it. So I'm going to come over to Desmos, and this is just desmos.com. This is what happens if you don't do any of the activities. You can go to desmos.com and click Graphing Calculator, and this will look somewhat like the Desmos Test Mode app that some of the distance learners have downloaded. So I'm going to add a table. So I click the plus button and table. And let's see, our first term. Let me just put in all the term numbers. 2, 3, 4, 5. That should be enough. Our first term was 5. 5? Yes. And our common difference was 3. So the next term is 8. Plus 3 is 11. Plus 3 is 14. Plus 3 is 17. And if I click on the zoom fit, I get those points that are in the table. Okay, so that's nice. So what about that function that we saw? Let's put in a function expression. So let's see, it was f of x equaled 5 plus 3x minus 1. And look, we've got a line that goes right through those points. So what if I simplify this expression? Right? What if I take out those parentheses? 5 plus 3x minus 3. You see what happened? I distributed this. Actually, let me go back to my slide so I make sure everybody's on the same page. Right, so if I want to get rid of the parentheses, I'm going to use my distributive rule. And I'll have 5 plus 3x minus 3. Okay, and then I can combine like terms. Right, I'd have 5 minus 3 plus, plus 3x, excuse me. 5 minus 3 is 2. If I rearrange this a little bit, I've got 3x plus 2. And that actually looks like an equation of a line, right? So f of x is equal to, what did we say it was? 3x plus 2. So I've got 3 different lines on top of each other, right? I've got a black line and then a red line and then a blue line. They're all the same line. And they're all going through those points that we got from our arithmetic sequence. And see, we could see here's our y-intercept, there's our x-intercept. This is a line. Okay, so that's what an arithmetic sequence looks like. Let's go back and look at a geometric sequence. So here's our formula for the nth term of a geometric sequence. Here's an example that I found. Again, the input's going to be n. So if we're going to write it in function notation, it's going to look like this. So let's go over to Desmos and see what this looks like if we graph this. So it's 2 times 5 raised to the x minus 1 power. All right. Two times 5 raised to the x minus 1. Now look at that. We talked about graphs like this at the very beginning of class, right? We talked about how some functions look like lines, some functions are long, smooth curves. This is an exponential function. And I can add a table, and I can put in some points. So at x equals 1, 2, 3, 4. We'll do a few points here. So when x is equal to 1, I get 5 raised to the 1 minus 1, which is 0. Anything raised to the 0 is 1. So that means my first term is 2. But I knew that already, right? That's what that first 2 means. All right, and then I'm going to multiply it by 5. So 2 times 5 is 10. 10 times 5 is 50. 50 times 5 is 250. And if I do a zoom fit, messed it up. Let me try it again. There we go. So there's 1, 2, 3, 4. So this is what a geometric sequence looks like when we graph it. It's an exponential function.